Hi everyone! Today is a half day Wednesday, and so we're reviewing, then we're going to play quizzes, and try to get you caught up with all the notes you might have missed on Monday or Tuesday. So in Unit 10, we worked on all the different wave behaviors of light. When light goes from one material to another, it might bounce off. It might bend because of the change in speed. It might diffract by bending through openings. It might just get absorbed, like when ultraviolet light gets absorbed by your skin. One that we didn't really talk about is scattering, but scattering is what makes the sky look blue. Right. Now, all of these pictures show light behaving like a particle or a ray. In rays, light travels in straight lines, and so in this optics unit, we're still talking about wave behaviors, but we're doing this with ray diagrams. These ray diagrams show light traveling in a straight line, instead of drawing the wave fronts or, transverse wave patterns. And one of the earliest evidence that light is a ray, that it travels in straight lines, is the camera obscura, which is literally just a hole, right? So let's say this is a very dark room. Light from the bright outside world would have some rays of light from the blue sky travel through the camera obscura and end up down here. Some rays of green light from the grass would travel through this opening and head up here. And the rest of this wall blocks out all the other rays, allowing an artist to paint an image, an inverted, real image on the back wall. So we now know light travels in rays. It travels in straight line paths. And it does this through lenses. A lens is a device that uses refraction to bend rays of light. Now, someone was asking, what's the difference between convex and concave? Well, that's referring to the shape of the lens itself. Convex lenses have sides that bend outwards. Concave lenses have sides that bend inwards like a cave. Now, I know you guys were all stuck on number 14 on homework 11.1. Those other types of lenses, you should know that they exist, like the meniscus and the plano-convex and the plano-concave. Please know that they exist, but these are the two that we're going to mainly deal with because these are the ones that we can use our lens equation, the lens maker's equation, and ray diagrams for. So we have two tools to study those and fewer tools to study the others, so don't worry about those too much. So from here, how do we figure out what these lenses do to the light rays? And for that, we actually need to think about what happens when light passes through prisms. In a triangular prism, refraction at these two boundaries, the bending once at the first boundary and once more when it goes back from glass into air, causes the ray of light to be refracted downward and disperse out into colors over here. Whereas when light goes through an upside down triangle, the ray gets bent upward twice due to refraction at both boundaries. This gives prisms their behavior. If you imagine a triangle prism placed on top of a rectangular and another triangle, well, this kind of looks like a convex lens, right? And a convex lens causes light to bend down, go straight, and bend up, converging on a focal point right around here. Right? So the convex shape must cause light to come together. Convex, converging. Similarly, let's make it the opposite. What if we did this? Okay, probably not the best picture. Maybe we'll do this with trapezoids. Right? This kind of looks like a concave lens. The sides of the lens bend in on both sides, but that causes light to travel away from a focal point. These two rays definitely would never meet up with each other. And notice it still causes that rainbowing effect. So there is a real life actual problem with lenses, and it's the reason that our main big telescopes, our Hubble telescope and our James Webb telescope, are not made with refraction. They're not made with lenses because with lenses, you always get a slightly blurred image. Notice in this case that convex creates converging, but see how the red, blue, and green don't all meet up in the same place because the light split up? The dispersion of light actually causes this rainbowing effect. This is undesirable and makes images a little bit blurry. For normal everyday use like cameras, that's not a big deal because the size of this aberration, this is called chromatic aberration. Chromatic aberration, like colors being distorted, would be too small for us to see. But on some big investment like the Hubble telescope or the James Webb telescope, that becomes a real problem. They actually use mirrors instead so that you don't have to deal with this refractive dispersion. Right? So, in short, convex creates convergence and concave creates divergence of light. And that's because of their shape. So one thing to note is that these rays are real. They literally intersect each other. And so this focal point is a positive, this focal length is positive. Focal length is measured from the center of this lens. So right here, center of lens to focal point. Someone asked me what's the difference between focal length and focal point. The focal point is right there. It's a position. The focal length is a distance. How far is it from the center to here? So no matter what this lens is doing, this always has a positive focal length because of its shape. Diverging prisms, however, concave always has negative focal length. So here's its virtual focal point. And it's virtual because in real life, the rays are not meeting. The rays don't physically meet up like they do with convergence. When it's diverging, our brain looks at these diverging rays of light. So imagine I'm standing right here, right? And I'm looking at the thing. Hey, I'm standing right here, I'm looking at the thing. My brain sees these 5 rays of light and thinks, well, light must have traveled in a straight line. The focal point appears to be here. So that's a negative focal length, no matter what sort of image is formed. So I'm going to ask about real versus virtual images. Real images occur when the light rays literally converge, like they do in your eye. The convex lens, and you actually have 2 convex lenses in your eye. We'll talk about the eye next week, but in case you want to feel them, close your eye, put your finger on top of it, and then look up and down. Yeah, you feel it, it's gross. Anyways, you have a convex lens, and that makes real images. And that's because the light rays get converged. In the back of your eye, you would see an upside down tree. So real images always inverted. Camera obscura also makes real images. And real images can be projected onto screens. So when a projector does it in my classroom, for instance, it starts with an image that's upside down. Then when it projects, a right side up image, but it's always inverted from each other, right? So very easy to tell real images apart because they're upside down from the original. Whereas virtual images are always upright and they can't be projected onto a screen. So let's say my eye is over here, right? I'm looking at this lens. Looking that way. I'm looking at these rays and they diverge, right? So my eye thinks they must have come from a place back behind the lens and it creates a virtual image. You'll be able to tell virtual images apart in a ray diagram because it'll have these dotted lines where your eye thinks the light came from. So in this case, my object is right here. So maybe this is the flame of a candle. But my eye would see that candle farther back behind the lens and much, much bigger. This is what a magnifying glass does, right? So virtual images are going to be not always larger, but they will always be behind the lens on the opposite side of your eye where the rays have diverged from each other. If you ever need to check if an image is real or virtual, probably a good check to do is the image upright? Virtual images, like when you look in a plane mirror, are always upright because they're virtual. There's no actual light here behind the mirror where your brain is perceiving this image. Virtual images actually exist in our brain because our eyes see the light from the mirror. And actually, these rays are drawn backwards, so don't believe this. This ray is drawn backwards and hits my eye. The red light leaves the car, hits the mirror, hits my eye. And my brain thinks that these rays that it just received must have come from back here, making a virtual image. So virtual images always upright. So we ended on Tuesday looking at ray diagrams. And ray diagrams are... So we ended Tuesday doing ray diagrams. And a ray diagram is a way for scientists to predict what an image will look like without literally going to get a pencil and an optics table and a lens. So how to draw ray diagrams is we know that parallel rays of light will either get converged towards a focal point or converged or diverged away from it. So imagine a parallel ray of light leaves the top of the pencil. This lens is a converging lens, so it would bend that ray of light towards the focal point. Whereas this ray diagram would be for a diverging lens, so a light ray that goes parallel in would have to go away from this focal point. Now, I'm drawing this line as virtual right here because this line isn't physically there. I'm using it to mark the distance between the focal point and the lens so that when I go draw this ray, which goes away from the focal point, I draw it in the correct path. So it's got to go away from the focal point in a straight line. But since this ray literally isn't there, I'm drawing it dotted for virtual. Okay? So either a ray goes towards the focal length or towards the focal point if it's a convex lens, or away if it's a concave lens. Then, a ray that leaves the top of the pencil and goes through the vertex of your lens right here, this point right in the center, would travel straight through without being bent at all. Now, that's because the two sides of the lens are parallel to each other at the center, at the vertex. And so a ray that goes through the vertex doesn't get bent. Right, so I'm going to try and draw that a little bit better. That definitely goes through the vertex right there. And one more. That one definitely goes through the vertex right there. Now let's find our image and classify it. So these two rays of light left the tip of the pencil. So that pencil must have a tip that's right where that intersection is. Make that a little bit easier to see. And my brain, because imagine my eye is on this side of the lens, I'm like looking that way. I'm looking through the lens. I would see this image. It's real, inverted, and smaller than the original pencil. But this time, I'm looking at these rays of light and my brain goes, those two rays diverge. And my brain thinks to itself, well, they must have come from back behind the lens. They must have come from here. And since those two rays represent the light from the tip of the pencil must be where those two rays intersect, virtually, back behind the lens, hence negative focal length, right? And I would get a smaller, upright, virtual image. So, quick comprehension check. Which one of these rays is drawn correctly? This was one of the questions on the homework that people got stuck on. Either a ray goes from the top of the object right through the vertex of the lens. So B is not it. That doesn't go straight. That doesn't work. Or it goes parallel in and gets converged towards the focal length. It's got to be D. This one goes parallel in and towards the focal point, which is right here. And then choice A, B, and C, those are just trash. Those don't actually obey either of those two, right? So fill in your notes with anything you might have missed from today. And why don't you go try the quizzes? Best of luck.